In this video, we're going to go over the last tab, Bobcat. So we're going to do our third one sample z-test. So again, whenever you conduct a hypothesis test, you want to start by reading the research description. So Bobcat Cruise Line Company wants to determine if their average customer satisfaction rating for their fleet differs from their industry standard. So the industry's average satisfaction rating is 8.5 out of 10 with a standard deviation of 0.8. So this is a population mean and a population standard deviation. So the company randomly samples 50 customers from various cruises and collects their satisfaction ratings. So we're going to use a 5% level of significance to see if the average satisfaction rating is different from the industry standard. So this is going to be, again, a one sample z-test. It is a one sample z-test because we have one sample and we are comparing that sample to a population mean. And then we're going to make generalizations about the populations. So our sample is the Bobcat Cruise Line. They took a sample of 50 of their customers, and we are going to compare that to the industry average, which is a population mean of 8.5. Basically, they want to see if they have different ratings than the industry average. They're going to take 50 customers to make a generalization about all of their customers. When we conduct this type of hypothesis testing, we are going to use the sampling distribution of sample means. Remember that sample means are normally distributed, so we can determine the probability or the likelihood of obtaining our sample mean, and we can use that to draw conclusions. So we always have two hypotheses. We have the null and the alternative. The null hypothesis is always the same. It's that there's no significant difference between our two groups' population means. So those two groups are equal. The alternative is the research hypothesis. So this is two-tailed. This was a two-tailed example. And the reason why is because they didn't specify in the research description. Again, remember, you can always find the alternative hypothesis in the research description, and they didn't specify if they're looking to see if their average score is greater than the industry or less than the industry. So they're exploring both possibilities, so that makes it two-tailed. So you might be wondering why we have the null hypothesis when really we're just interested in the alternative hypothesis. And that is because the null hypothesis is concrete and objective. The null hypothesis is that the population mean for Bobcat equals the industry average, which is 8.5. The alternative or the research hypotheses, these are always ambiguous. So we think that it's different. We don't even know how it's different. We don't know if it's greater than or less than. But let's say we had predicted that it was greater than. Let's say we think Bobcat's doing better than the industry average. By how much? We would have to specify by exactly how much in order to test that. So the alternative hypotheses are always ambiguous, especially in the case of a two-tailed hypothesis. So that is why we test the null hypothesis. We're going to look to see if if it looks like the Bobcat's mean is 8.5. If it's not, then we'll say that it's different. So we always test the null hypothesis, even though we're really interested in the alternative hypothesis. All right, so let's go down and start to perform our calculations. So the industry average, this is our population mean. It's 8.5 on a 10-point scale. The standard deviation is right here in our research description. It is 0.8. Now for the Bobcat Cruise Line, we have sample data, and it's over here to the left. So we'll use the average function to compute the mean. We'll use the count function to determine the sample size. And then we can compute the standard error, which again is sampling error. And it is the average difference between a sample and its population mean. And the formula is the standard deviation divided by the square root of the sample size. And we got 0.11. And again, you can see it's everything's starting to pop up on the chart. So this is our population mean. It's 8.5. And then you can see we can go out by one standard error. Again, the standard error is 0.11. So here's one standard error below to one standard error above. And 68% of samples will have means between these two values. All right, now we want to determine our cutoffs or our rejection region, right, when we're going to reject the null hypothesis. So alpha, or the significance level, will always be provided in the research description. Ours is 0.05 or 5%. And that is our rejection region. So we are going to set it up here. We're going to have a left rejection region and a right rejection region. And that's because we're doing a two-tailed test, right? We don't know if Bobcat's going to be less than the industry average or greater than the industry average. So we're going to look in both tails. So because we're looking in both tails, we have to divide alpha into two. So we're splitting alpha into each of the tails. Now let's find the z-score that's associated with those two tails. So for the left, we're finding the z-score that cuts off the bottom 2.5%. So that's our norm.s.inv, and then we reference our probability or alpha. And then for the right or the upper, it's norm.s.inv 1 minus our probability or alpha. And I got negative 1.96 and positive 1.96. So here it is on our graph. This is the bottom 2.5% and the top 2.5%, and it's marked by our critical values. You'll notice that the critical values are the same, just negative and positive, and it's always going to be like that. And the reason why is because we're working with a symmetrical bell-shaped curve. So the score that cuts off the top 2.5% is going to be the same as the score that cuts off the bottom 2.5%. It's just going to be negative. All right, let's change our z-scores to raw critical values. So what is it in terms of like actual units of measurement? So we take our population mean plus our standard error times the z-score. So the lower cutoff is 8.28. So if we observe a sample mean below 8.28, we'll say that Bobcat is lower than the industry average. And then the upper one is the population mean plus the standard error times the z-score, 8.72. So if we observe a sample mean above 8.72, we will say that Bobcat is greater than the industry average. Again, it's very rare, very unlikely that we would observe a sample mean in either of these tails. So if we do, it suggests this is not what's going on. The Bobcat average is not 8.5. If we observe a sample mean in this white area, we'll say, okay, that's just sampling error. It's to be expected. The mean is 8.5. So let's see what's going on with our Bobcat sample. We got 8.75, which is above our upper cutoff. So let's compute the test statistic. So the formula for the test statistic, or the standardized z-score for our sample mean, is the sample mean minus the population mean in parentheses, and then divide by the standard error. 2.21. So I can see it right here. We can move this little box over, this text box, if you can't see it. Might be a little bit hard to move, but you can move it. And this is our sample mean. All right, what is the probability or the percentage associated with our sample mean? Well, this is tricky. It's tricky for a two-tailed test. And if you look up here, you can see that you have a p-value for the area to the left, and you have a p-value to determine the area to the right. So when you do a left test, you just always do the left p-value. When you do a right test, you just always do the right p-value. When you do a two-tailed test, you have to determine whether you're going to use the one to determine the area to the left or to the right. So you can look at the graph. You can see that we want to determine the shaded area, which is the area to the right. And it says right here, we want the area to the right. So you always want to figure out the tail, which is the smaller part. So we are going to figure out the area to the right. So that's 1 minus norm.s.dist. And the only difference between the two is the area to the right. To determine the percentage to the right, it's 1 minus. And to determine the area or the percentage to the left, it's just norm.s.dist. So that is 1 minus norm.s.dist. And then we reference our test statistic and then true. Now, if you find this very, very confusing, what you can do is you can compute both. And the p-value for a two-tailed test, it's always the smaller of the two. And again, this only applies for a two-tailed test. So for a two-tailed test, you have to determine which one to use. For left and right, you don't. You just use, for a left test, you use the left one. For a right test, you use the right one. It's only for a two-tailed test that you have to determine which one to use. And it is always the smaller of the two. So we are going to go with 1 minus norm.s.dist. Okay, you can see that we are going to reject the null hypothesis. So our sample mean is greater than that upper cutoff. The test statistic is greater than the upper critical value. And the percentage is smaller than that alpha. So you can see all three comparisons, and they're all going to be obviously always in agreement. But all of them there are saying to reject the null hypothesis. So we're rejecting that the mean is 8.5. And we believe that Bobcat's mean is greater than 8.5, right? It's very unlikely that we would observe a sample mean in this tail. So that suggests that Bobcat is not part of the industry average. They're higher than the industry average. All right, so let's do our p-value approach and our critical value approach. We've already discussed this, but we'll just go through the questions. So again, the test tells you whether to reject or fail to reject the null hypothesis. There's two approaches. One's the p-value approach, one's the critical value approach. Both are in agreement because we're comparing the same thing. It's just whether we're comparing standardized scores or percentages. So for the p-value approach, we are comparing percentages. So what's our alpha? So since we had a two-tailed test, we had to divide alpha by 2. So we use a 2.5% as our comparison. Right? That's what we're using in our approach. And then the p-value was 1.4%. And our p-value was less than alpha. Whenever your p-value is less than alpha, that is when you reject the null hypothesis. Remember, when the p is low, the null must go. All right, now we can do our critical value approach. So we can potentially have a lower and an upper critical value. And for a two-tailed test, you have both, right? You have a left critical value and you have a right critical value. And that's because you were looking in both tails, right? We were looking to see if there's a difference. So we were looking in both the left and the right tail. And we compare our test statistic for the sample mean to those critical values. So that's 2.21. And what did we find? We found that our test statistic fell in the rejection region, right? It fell in that red shaded area on our chart. So it fell in the rejection region. So we are going to reject the null hypothesis. All right, so what does this mean in everyday language? Whenever you reject the null hypothesis, that means you found a difference, right? The null hypothesis is that the means are equal. So if you were rejecting that, that means you found a difference between your two groups. So what kind of difference did we find? Well, we found that Bobcat is greater than the industry average. So we found data that indicates Bobcat is significantly greater or more than the industry average. And again, this applies to the population mean for Bobcats. Even though we only sampled 50 customers, the test is telling us that we can generalize that conclusion to all of Bobcat's customers, so their entire customer average. And since we rejected the null hypothesis, we would say that our test is statistically significant. All right, now let's answer our conceptual questions. So the first question asks about sampling error. This is our standard error. So remember, the standard error tells us on average how much we would expect a sample mean to differ by the population mean. So we found a standard error of 0.11. And then what percentage is going to be within 3 standard errors? That's 99.5% of samples. Their mean is going to be within 3 standard errors. So what's that in our example? So again, here's the population mean of 8.5. Here's 1 standard error, 2 standard errors, 8.27 to 8.73, and then 3 standard errors is 8.16 to 8.84. So 99.5% of samples are going to have means between 8.16 and 8.84. All right, what was the upper cutoff for rejecting the null in raw values? So again, this is the upper rejection region in the right tail, and it was marked by a critical value of 1.96. But the question was asking about it in raw units, and that was 8.72. So that's right here on the chart. So this was the critical value in raw units. So we can reference that. That is 8.72. So we said if our sample mean was greater than this, that's when we would reject the null. And our sample mean was 8.75. So we rejected the null hypothesis. All right, the last thing we'll do is the confidence interval. So we are going to compute the confidence interval for the population mean for Bobcat. We know the sample mean based off of 50 customers, but we want to know the population mean for all customers. So to do that, first we got to compute our margin of error. So we start the margin of error with the critical value for a two-tailed test, which is norm.s.inv, and it's 1 minus alpha divided by 2, close your parenthesis, and then multiply it by the standard error. All right, now we can use this margin of error to build our interval. So the lower is the sample mean minus the margin of error, 8.53, and the upper is the sample mean plus the margin of error, 8.97. So we are 95% confident that the population mean for Bobcat is 8.53 to 8.97. You can see that estimation is above the industry average of 8.5. And it has popped up on the graph. So this green line, again, it's this interval based off of our sample mean. Our sample mean is this gray line. And we have this interval. This is the estimation for the population mean for Bobcats. All right, so let's answer our last 2 questions. What are we estimating with the confidence interval? We are estimating the population mean for Bobcats. And we found that we are 95% confident it's between 8.53 and 8.97. All right, that is it for the Bobcat tab.